Okay, hello, welcome. We're going to be looking today into support vector machines and neural networks. The roadmap for the class, we will first look into the theory behind support vector machines. And specifically, we're going to be looking first into the simpler example, which are linear SVMs, and then we'll look into the non-linear approach, and we will finalize looking into multi-class SVM. So basically, support vector machines were designed for binary classification problems, so we will see how we can scale up this for a multi-class setting. And then we'll also be seeing neural networks. So support vector machines are discriminative classifiers. Remember that a while ago when we started looking into classifiers, we differentiated between generative and discriminative classifiers. For example, naive Bayes are a type of generative classifier. Logistic regression is a type of discriminative classifier. The general understanding, if you recall, was that discriminative classifiers tend to look for decision boundaries that separate the two types of classes, whereas generative models tend to probabilistically model the relationship between the features and the labels. So in the case of support vector machines or SVMs, and these are a type of discriminative classifiers simply because of the way they are designed in such a way that they look for decision boundary that maximally separates the two classes. Okay, so basically the simpler version, as I was saying, we're going to assume that the classes are linearly separable. That's the simplest case. And if we assume that, basically what an SVM is going to do is look for the boundary that maximizes the distance between the two classes. That's what it's also called the margin. If you look at the plot on the right hand side, this is a general idea, right? So you have different circles, which are class one type of class, and you have different squares, which are another type of class. And we want to basically classify these. Okay, we want to build a classifier that will separate circles from squares. So if we want to do this with support vector machines, basically we assume that the two classes are linearly independent, then basically we're looking for a hyperplane, and I have drawn there several of them, but we are looking for a hyperplane that maximally separates the two classes. Okay, so what we're going to do is select a hyperplane in such a way that the distance between the hyperplane and the data points that we have in our sample is maximalized. And we want to maximize basically the distance between these two, right? So what I'm showing in this plot two are, if you see the two lines that have 3 squares and 2 circles, those are the support vectors. Okay, so support vector machines are called like that because they basically do is they look for the support vectors within the training data set that we have, and the support vectors are nothing else than just a few of the training data points that we have, and those training data points are basically the ones that define where the hyperplane, the separating hyperplane, should be located. Okay, so basically the decision function that to define the separation between the two classes does not depend on all the samples, but rather only on the support vectors that we are working with. And because this is basically a problem in which we need to maximize the margin that exists between the two, we'll see, I'm going to elaborate on that in the next minutes, but we'll see how this is in reality a quadratic programming problem. So again, if we assume linear separability in 2 dimensions, basically we can separate classes with a line. If it's more than 2 dimensions, then we'll be talking about hyperplanes. That's the reason why I said that we're looking for the hyperplanes that maximally separates the two classes. And so if we are gonna be solving this problem with quadratic programming, basically let's frame it as an optimization problem, and you'll see better why. Okay, so if we frame the problem as an optimization problem, again we have 2 different types of samples. In this case we have red circles and green circles. So we want to find the problem can also be defined in such a way that what we want to do is find A, B, and C such that these 2 conditions are respected. Okay, so the first condition, ax plus by is larger than c, is respected for the red points, and the second condition happens or is verified for the green points. Okay, this is what we are looking for. Exactly what we are looking is that whenever we are working with a red circle, that red circle, those values are going to be larger than c, and on the opposite case they're going to be smaller than c. We are looking, for that line or that hyperplane that can separate these 2 types of samples. And as I mentioned before, these hyperplanes can be many. Okay, we have many. We have, in principle, we could have different solutions for A, B, and C. Okay, and so what we want to look for basically in that separation are the support vectors, which are the elements of the training set that could change the position of the dividing hyperplane if removed. Okay, the hyperplane search can be understood as just looking for those support vectors that are gonna determine where the hyperplane goes. And in fact, those support vectors, okay, are the critical ones. So we can move any of the other samples around and nothing will happen. But if we move the support vectors, the hyperplane will also change position, and the boundary and the margin will also change. Let's look at it more formally, okay? And let's frame the problem as I was saying before. Again, we have the red circles, we have the green circles, okay? And we are looking for that hyperplane H that maximally separates the two types of samples. Okay, so if we have a hyperplane H, we're looking for a hyperplane that's, for a given set of x's and weights plus b, it's larger than 1 when y equals 1 and is smaller than minus 1 when y equals minus 1. Okay, so imagine that the red dots represent a plus 1 and the green dots represent a minus 1. This is our binary classification problem. So basically the hyperplane that we are looking for is the one that basically separates these two types of samples based on their labels, right? Now, we are looking for that H, but basically the H that we are looking for, okay, we want to be looking for one that will maximize the margin, that will maximize the separation between the two data sets, right? So we are looking for an H that, if you look at the plot there, we are looking for an H that maximizes the margin, okay? So basically that maximizes the sum of D plus and D minus. We're looking to maximize that distance between the two. Okay, and exactly between which two? So exactly between two planes that we define as H1 and H2. Okay, so H1 can be defined again as x multiplied by w, where x is different x values and w is the distribution of weights, plus b equals plus 1 for the plane that represents the red dots, and then on the other hand H2, which is x multiplied by w plus b equals minus 1, represents exactly the other plane, the plane H2, that has 3 support vectors in it, and that basically helps characterize the second class, the class of the green circles. Okay. And again, H2, the plane H2 has 3 different support vectors, and the plane H1 also has 3 different support vectors. So formally, what we are trying to do, what support vector machines try to do when we have again the simpler scenario, which is a scenario in which the classes are linearly separable. Okay, so we are just trying to maximize that D plus and D minus distances. We are looking for that hyperplane H that will maximize that distance. And this is also very important, to understand if the support vectors are moved, the decision boundary is going to be moved, okay? Because the hyperplane is defined with respect to the support vectors. So on the left-hand side, the plot on the left-hand side, you see a case in which, we had two planes defined, and basically the hyperplane was the dashed black line, and we had one plane with two green dots and then the other plane with 2 green squares, and then suddenly we move one of the dots, one of the support vectors, and of course the decision boundary is going to change. Okay. Whereas in the plot on the right hand side, we observe the opposite situation in which we move a data point, but it's not one of the support vectors. So in this case, it doesn't matter. The decision boundary or the hyperplane that SVM computes is exactly the same. It's still the dashed black line, because the support vectors have not been changed. So in reality, if we go back a couple of slides, so in reality, what support vector machines do, okay, they basically do a lot of linear algebra, okay, and what they try to do is just, again, maximize the distance between the data points and the hyperplane. We try to maximally separate the two classes, okay? So formally, we'll see how we can solve this problem of maximally separated the two classes. But before we do that, let me just refresh some algebra just to make sure that we are all on the same page. Basically, I'm showing how to compute the distance between a point and a line. Okay, imagine that we have an ax plus by plus c equals 0. That's the black line that we have there. And so if we have a point x0 and y0, and we are trying to compute the distance between that point and the line, the way this is computed is with the formula that you see below there. So the distance equals ax0, x0 plus by0 plus c divided by the square root of a squared plus b squared. Okay? That's the formula for the distance. And this is important to know because remember that what SVMs do is that they maximally, or they want to maximize the distance between the points in each class and the hyperplane. Okay, so we will need, obviously, to be able to compute the distance between each point and whatever hypothetical hyperplane we are exploring. If we go back to the example, to the plot that I was showing before, in which again we have the red circles, green circles, we have h1, h2 with the support vectors, and we have h as the hyperplane that's going to maximally separate the two data sets. Again, what we want to do is basically maximize the d plus d minus distance, maximize the distance between h1 and h2, right? So how do we do that? Again, if we compute the distance from a point to a line as what I just explained in the previous slide, then the distance between h and h1 is going to be computed with the formula that you see there. Okay, basically the distance between the points that we have in h1 and the hyperplane h can be computed like that. Okay, why? Because we basically have remember that the hyperplane h, the formula that represents hyperplane h is w multiplied by x plus b. So that means, you know, the different x features that we have multiplied by the weights. Okay, and so basically that's going to be the function that we fill with any given point, and then we divide by the norm. So the double vertical line represents the norm, or in this case the Euclidean norm, which is basically the length of the vector. Okay, and so we can rewrite that as 1 divided by the norm. Okay, so if the distance between h and h1 can be written as 1 divided by the length of the vector, by the length of the w vector, the vector of weights, then the distance between h1 and h2 can be represented as 2 times that. Okay, and that's exactly that distance, that margin is the one that we want to maximize. Okay, so we can frame the problem now as a maximization problem, okay, in which we need to maximize 2 over the norm of w. And we have a couple of conditions. The conditions that we have is that whenever we have a label of plus 1, x multiplied by w plus 1 has to be larger than 1, and whenever we have a label of minus 1, the same condition has to be smaller than 1. So what we are saying is we want to maximize that distance that separates, you know, the points from the hyperplane, but at the same time we want to make sure that the two classes are fully separated. Okay? Okay, so this problem then can be formulated, as I mentioned a few slides ago, as a quadratic optimization problem. Okay, again, remember that the only thing that we need to find here are the weights. Okay, and basically what we need to do is, given the previous formula, remember that the distance between h1 and h2 is 2 over the length of w. So basically we need to maximize that distance, or considering the dual problem, we can minimize 1/2 of the square of the norm. Okay? And of course, always taking into account that the condition of w x plus b is larger than 1 or smaller than minus 1, given that y is plus 1 or minus 1. Always taking into account that we are separating the two distinct classes that we have. And this is exactly what, whenever you run a software package for support vector machines, this is exactly what's happening, okay? So what's happening is that given all the data points that you have in your training set, basically SVMs are going to be looking for the distribution of weights, okay, that characterize that hyperplane that maximally separates the two distances. Again, remember that if you look at the plot here, that h hyperplane that we are looking for is basically characterized by a set of weights w and by a value b. So that w and b, those w and b are the values that we want to find. Okay, and we want to find them in such a way that the margin is maximized and that the conditions of the labels are also completed. Of course, I mean, this problem is just an optimization problem and it can be solved with quadratic optimization. Okay, nothing complex here, and this is exactly what goes on. However, this is an ideal scenario, right? Because what happens oftentimes is that they are not perfectly linearly separable, okay, the samples that we are working with. So the example that I'm showing here is just like there's one red sample on the other side, there's one blue sample on the other side. So I mean, they are not completely perfectly linearly separable. Okay, so then what is it that we do? So we define what we call the slack variables. Okay, the slack variables are basically added to those variables that are, say, on the other side. And instead of talking about classification or pure separation, we are going to be talking about soft margin. Okay, we are going to be maximizing, rather than the margin itself, we are going to be maximizing what we call the soft margin. So in this case, instead of looking to minimize, remember that again, we are looking for the hyperplane, we are framing it as an optimization problem, looking for the weights and the value of B that maximize the distance between the samples and the hyperplane. So in this case, again, we define it as a minimization problem with 1/2 of the norm of W of the squared norm of W. But what we do is that we add a summation of the slack variables. Okay, so, and again, the conditions that if given the label +1 or -1, the value of the hyperplane is also going to be +1 or -1. So the philosophy is the same. We are minimizing exactly the same thing, but we are adding the slack variables, okay? So that, we take into account the fact that there's going to be noisy samples. And we also add a control parameter, C. And that control parameter, it's basically put there to control overfitting. So what basically C is doing is control the importance of maximizing the margin and fitting the data, okay? So how well do we want to fit the data that we have to separate the hyperplane that separates the two? With respect to maximizing the margin. Okay, so what's more important? Is it more important that we respect, or the margin that we find maximizes the distance but with some points off, or it's the opposite? So what C is doing is exactly that. It's basically like a trade-off button that we have there, and we will have to, on one hand, measure the importance of maximizing that separation, and on the other hand, the importance of fitting the training data. If you look at that formula that we need to minimize, it probably brings some memories when we studied linear regressions and regularization methods, remember? So it's something quite similar. Okay, so we try to add yet another control element there, okay, that will allow us to basically control for overfitting. So it's important that we fit all the points, but maybe, some features are not as important as others. So that was what regularization was doing. Here is something similar. Okay, so maybe it's important that we maximize the margin, but and that we fit the data, but maybe not all the data needs to be fitted, and that's what the slack parameter says, and C controls for that. Okay, so this is just, I think that I already mentioned that when I was discussing that SVMs are a discriminative method. So SVMs or logistic regressions are discriminative because they basically look for boundaries, for separation boundaries between the two classes. In the case of SVM, it's looking for a hyperplane that maximizes the margin. In the case of a logistic regression, it's looking for a hyperplane based on conditional likelihood. Okay, so there's some probabilities there, but in the end, it's just like a decision boundary. So that's the reason why logistic regression is also discriminative. And then something like naive Bayes, the separation hyperplane, or how we consider one class or another one, it's based on joint likelihood. So it literally takes into account at the same time both features and labels. And so that's the reason why it's a generative model. Okay, so far we've looked into linear supervector machines. So we have assumed that the data points that we had in the two classes, or actually that the two classes were linearly separable, okay? But that might not be always the case. Okay, so sometimes we have data sets that might have some noise. That's fine, we've seen how to cover that, but sometimes literally it's just impossible to find a linear separation between the two. Okay, so that's when mapping the data to a higher dimension actually helps. And in fact, this is where nonlinear SVMs come in. Okay, so the original idea is that, we have the plot on the left-hand side. There's no way that we could linearly separate the red dots from the blue dots. So why don't we just map the samples that we have to some higher dimension feature space, where we can actually find a hyperplane that will separate the two types of data points. So remember when we described how to solve the optimization for the quadratic optimization for the linear SVM? That basically, we had a set of formulas there. I didn't go into details into how that is solved, but basically in its solution, there is, or it's based on the inner product between xi and xj. Okay, and so in order to find the optimal solution, we need to compute that inner product. However, that inner product and the optimization of that inner product becomes really complicated when the samples are not linearly dependent. Okay, and so in that case, what we can do in support vector machines is to basically transform the data point x into a high dimensional space, okay, and we just do some transformation on the point, and then that inner product becomes an inner product of the data points that have been transformed. And in that case, solving the optimization is going to be easier, right? And that's what we call the kernel trick in SVMs. Okay, a kernel is just a function that allows us to do the inner product, but in other feature space than the one that we originally had. The interesting thing about kernels is that they are useful because when we have a non-separable problem, it typically makes them separable. Okay, so by just the data points that we have to another dimension, it basically converting the data points that we have to another dimension, it basically allows us to separate them. The linear support vector machine, I mean, we could also talk about a kernel there, okay, and basically it's just the inner product of the transpose of the vector and the vector itself, okay. We could be talking about a sigmoid kernel, we could be talking about a polynomial kernel, we could be talking about a radial basis function kernel. In any case, what these are just different types of functions, okay, to represent the inner product that the linear kernel represents. So to give you just an example of where linear kernels don't do anything and Gaussian kernels actually help. So it's this one here on the left-hand side. You see the square and the red dots that are impossible to separate linearly, and on the right-hand side you see how we can actually separate them with Gaussian functions. Okay, and in general, we'll see an example with that, but in general, in the literature, it's been reported that radial basis function kernels are the ones that typically work the best when the classes are not linearly separable. Support vector machines can only handle binary classification problems, right? So what happens when we have more than two classes, right? I mean, the way SVMs mathematically work is that they try to look for hyperplanes that separate two different types of data points. But what happens when we have more than two types of data points? This is not a problem of being linearly or non-linearly separable, right? I mean, this is not something that the kernel trick is going to help with, but it's, what do we do when we have multiple types of labels there? So there are two different scenarios, two different approaches have been used to scale SVMs to multi-class settings. It's the one versus all and the all versus all. The one versus all basically creates one binary classifier per class. So it's as if you have, say, classes A, B, C, and D, you create one binary classifier that classifies whether it's A or non-A. Okay, you create one binary classifier that classifies whether it's B or non-B, C or non-C, and D or non-D. Okay. So if you have, say, an X classes, and then you will have X support vector machines. Okay, the number of classes that you have is exactly the number of support vector machines that you're going to have. On the other hand, the one versus one approach, what it does is that it creates one binary classifier for each pair of classes. So it would create one binary classifier for A versus B, one for A versus C, one for A versus D, one for B versus A, and so on. Okay, so once you have all these classifiers, basically the one with the highest number of votes is the final label that wins. However, as you can imagine, the 1 versus 1 is much more expensive because of the explosion of different combinations between labels that you have. Okay, graphically this is exactly what I just said. The 1 versus all, you're going to have a C versus not C, or D versus not D, whereas in the one-on-one you're literally comparing each two possible pairs of classes. And finally, I just wanted to mention the fact that although we've just focused on binary or multi-class classification problems when we've been discussing, the theory behind support vector machines, SVMs can also be used in regression settings. Okay, so we'll see when we look into commands to execute R, you'll see that we will have, there will also be a label that you can specify as of whether you want to run it as a support vector machine or as a support vector regression. Okay, in both settings, those are two settings that you can actually execute with SVMs.